The previous session we found a wave function for the case when the incoming particle was outside the well, outside little r radius a. So we got an expression b naught sine of kr plus delta naught all over little kr. Well, inside the well we'll get a similar Schrodinger equation, very simple form of this form, second order differential equation, with a big K squared instead of little k squared, where big K squared is defined as twice the mass into big E plus V naught all over h bar squared. So you can solve that in the following form. No deltas this time. So here's your solution to this Schrodinger equation. Okay, so we have two wave functions, one inside the well, the other outside the well, and now at the boundary, at the edge of the well, r equals a, these two, like I was saying in the previous session, these two have to match, their values have to match at r equals a, and their gradients at r equals a also have to match. So do this as homework. You'll get something like this, right? So do that. You know, this is matching. Well, this expression comes from your two conditions where the values match and the gradients match, and from that you'll get a sine term, and you get one form with sines in it and get another form with coses in it. So manipulate those two equations and eventually get this. You've done this sort of thing before, so do that for homework. Now, interestingly, if you got this, we now have an expression for delta naught. We can actually calculate what that phase change is, and that's interesting because if we know the delta, then we can find f of naught, stuff like that. So once we know what the delta is, we're a whole major step further along. Right. So again, as homework, given this, find a formula for delta 0, and it works out to be this. So do that for homework. So delta naught then is the r tan, the inverse tangent of little k over bk, tangent big K of a minus little k of a. Right? Now we had a formula before, the total cross section, little sigma, is 4 pi over little k squared sine squared delta naught. But we now have a formula for delta naught. Okay, so plug this formula for delta naught into the formula for the total cross section, which I'll say it again. So little sigma is 4 pi over little k squared sine squared delta naught. But now we plug that in, so we now get this expression. We now have a formula for the total cross section. Now, just as a check, if the here I'm using an O, so it's clear that it means potential. So if the potential inside was not being consistent, was equal to the potential outside, then bk and little k would be equal. If that's the case, then delta naught would be 0. Let's just check that. Why does that make sense? Okay, get it from here. So if the two potentials are equal, inside and outside the same potential, then big K equals little k. And where's that come from? So bk squared is twice the mass E plus V naught over h bar squared, and little k squared, I haven't written it up. Anyway, okay, so assume bk and little k are equal. So this is 1, and therefore you have r tan of something is just something, right? The artan and tan cancel. So you're just left with a something, which is big K over A, but big K is equal to little k's, so you're just left with little ka minus little ka, which is nothing. So delta naught is nothing. Okay. So if the two potentials are equal, inside is outside, there's no phase change, hence no scattering, which sort of makes sense. Okay. So you know. Now we assumed earlier that little ka is much less than 1, and from that we got the S wave scattering. That little l was 0. Okay, but big Ka that can have any value, and that value, big Ka, depends on the depth of your well V0. Okay? So now we can start solving numerically some interesting equations. So if little Ka, we plug in a certain value, okay, so if we choose a value here, this is pretty small. It's a lot. So what? 20 times smaller than 1. So let's say little Ka is this particular value, 0.05. All right. Then as big Ka, we draw this graph here. So as big Ka, every time it goes past, as its value increases beyond an odd number, an odd integer number, multiple of pi over 2. So the unit along this axis, dimensionless, is Ka over pi. So this value is just along this axis. It's just Ka divided by pi. So 1, 2. So just in units. But when Ka is an odd integer number of pi over 2, then it'll jump up. So you're at these values, a half, 1.5, 2.5, 3.5. Then along this axis, you have values for your delta naught divided by pi also. And so this dotted line here, so it jumps at when big Ka becomes an extra odd number, integer number of pi over 2. It'll jump up by 1, 1 unit. So along this axis is the value of your delta naught, your phase change, delta naught divided by pi, right? Delta naught divided by pi. So as your Ka, big Ka, keeps increasing, so does your phase change, but in jumps, right? So it just stays at at 1. So delta naught would be pi. Just stays that value until the next, until Ka increases by a certain amount, then jumps again, and so on. And this graph comes from this equation. Okay, you can solve that numerically. So as this keeps increasing, Ka, when it goes over an odd integer number of pi over 2, then your delta will jump. Okay, so you take this formula and put it in graphical form, and you'll get this. Right? So for what values of Ka do you get the total cross section, little sigma equaling 0? So that's this equation. Okay, so for what values of big Ka here, given little Ka is this value here, so you know that little k, so for big K is this. All right. So for what values of big Ka do you get sigma equaling 0? Well, you can do that numerically. You need a computer to solve it. You get these values here. You have 4.49, and 7.72, and 10.9, 14.06, and so on. Now, interestingly, if you look at the separation between these values, they're almost pi. So roughly a pi separation. So when these cross section, the total cross section, little sigma, when that's 0, how do you interpret that physically? What's going on? Well, there's an effect called the Ramsauer-Townsend effect, and what that means is if you have electrons and you're sending them through a helium gas, then for a certain energy, in other words for a certain big K, so if the energy of the electrons is about 0.7 electron volt, then no scattering. They don't scatter, which is sort of odd. You'd expect them to scatter, but they don't. And that non-scattering at that particular energy is called the Ramsauer-Townsend effect, which was surprising, but it comes out of this scattering theory. Okay. Well, as usual, run out of board. So next we'll do the repulsive case, not the attractive, and it changes the mathematics a little bit, but we can use this analysis pretty much, just make a few changes and come to do the other case, not the attractive case potential, but the repulsive case. So stop there.